we're looking at solving exponential equations. And we're going to actually do this using two different methods. We're going to start today by solving equations using the same base method, and then we're going to solve equations using logarithms. So to help us get started here with the first method, I'm going to have you actually go ahead and work through questions 1 through 4. So you're going to begin by filling in this table of values. You can grab a calculator if you need that for any of these, but maybe see how many you're able to fill in without a calculator first. And then we'll go ahead and continue all the way through to the end of question 4. All right, so we're going to come back together here and check in on those first couple of questions. So this is how we should have filled out our table. A couple of things here in the table. Notice how every time we have our value, a number raised up to the power of 0, it's always equal to 1, so that whole top row is the same. And then going down the columns, so like when we have a base of 2, for example, the only thing we're doing to get from one value to the next is we're just continually multiplying by 2. In the next column here, when we have a base of 3, we just continue to multiply by 3, and so on. And so having reference to this table is going to help us with our first method for solving equations today. So we have a pretty simple equation here to start off. We've got 2 to the power of x equals 2 to the power of 3. So hopefully here you noticed that these two sides have something in common. So both the left and the right side have a base of 2. Holding up an exponent. And so if 2 to the x is equal to 2 to the power of 3, well, then x must be equal to 3. So basically just setting our exponents equal. So it's the only thing in the two sides, or the part that was different, x must be 3. All right, so let's take a look at something in the next problem here. So we've got 32 equals 2 to the power of x. And we're going to try to solve this equation to make it look the same way as the previous problem. And so we're going to take a look at this left-hand side, and we're going to rewrite this with a base of 2. And so if we look back up here at our table, we can see that 32, sure enough, it's in the table for the powers of 2. It's 2 to the 5th power. And so instead of keeping it as 32, we're going to replace that with 2 to the 5th. And now we have a really similar situation. So we've got a base of 2 on both sides. So we're going to set the positions of the exponents equal to one another. So if we set our exponents equal, we end up getting that 5 equals x, or x equals 5. All right, so then for number 4, solving this next equation, we've got 3 to the power of x equals 81. So notice that now on this side, this problem, we have a base of 3 on the left, and so we want to turn the right-hand side into something that also has a base of 3. So if we take a look at the second column of our chart up here, we can see that 3 to the 4th power is 81. We're going to rewrite 81 as 3 to the 4th. And now that we have the same base on both sides, we'll go ahead and set the exponents equal. And so for this problem, we end up getting that x is equal to 4. All right, so those were some pretty simple examples of using the same base method. The situation can get a little bit more complex, so we're going to continue looking at 2 more examples that utilize this idea of solving. So looking at something like 8 to the power of 2x equals 32. So if we look at the left-hand side here, notice how we have a base of 8. Well, on the other side, we can't write 32 as something with a base of 8, right? So 8 to the 1st power is 8. 8 to the 2nd power is 64. 32 is like right in the middle there. And so rather than trying to do it with a base of 8, sometimes we change the base on both sides. So what I am going to be looking at is how could I write both 8 and 32 as something that has the same base. And so going back up again here to our table, notice how both 8 and 32 are found unknowns in this first column. And so we can write them both as 2 raised up to the power of something. So we could rewrite 8 as 2 to the 3rd, and we could rewrite 32 as 2 to the 5th. So sometimes it's both sides that we're changing. Now let's be careful on this left-hand side. When we rewrite that 8 as 2 to the 3rd, I want you to put that 2 to the 3rd in parentheses, because it's still then being raised up to the power of 2x. And so for now, we're going to have that 2x on the outside of our parentheses. Now there is a property of exponents that says if you have something inside parentheses like this, and it's being raised up to another exponent on the outside of the parentheses, what happens is that those exponents multiply together. So it's really, in this case, it would be the same thing as a to the power of m multiplied by n. And so that's what we're going to have to do here with the 3 and the 2x. I'm going to make a little note here that we need to multiply. And so 3 times 2x turns into 6x. Got 2 to the power of 6x. On the other side is equal to 2 to the power of 5. All right, as soon as we have our bases the same, so we have a base of 2 on the left, we've got a base of 2 on the right, all we need to do now is set the exponents equal. So 6x must be equal to 5. And then we'll finish it out by dividing both sides by 6. It's actually very common using this method to get an answer that is a fraction. Just go ahead and leave it as a fraction. You don't need to turn it into a decimal. And that's our final answer here would be 5/6. All right, and then we have another kind of situation over here on the right-hand side. Let's take a look at our bases at the very start. So notice how we have a base of 3 on the left side. We've got a base of 27 on the right side. So certainly it's not the same base at the very start, but this one is actually going to be very easy for us to get them both to be the same base. So if we think about a base of 3 and how that relates to 27, 3 to the 3rd is 27. So that's one of our values right here in our table. So the only one that we're going to have to rewrite is the right-hand side. And just as we did before in the other problem, when you replace 27 with 3 to the 3rd, I want you to put that 3 to the 3rd in parentheses, because it's still being raised up to this 5x plus 1 exponent. That's still going to be on the outside of our parentheses. Now, in the last problem, just as we had the inside and the outside exponents multiplied, exactly the same thing will happen here. But because of that plus sign, it's going to be the distributive property. So you're going to do 3 multiplied by 5x, and we're also going to do 3 times 1. So if I wanted to write this whole thing without parentheses, it would be 3 to the power of 15x plus 3. A really common mistake that students make on this is they don't write plus 3 here, they accidentally write plus 1. So make sure we know that that 3 is being distributed, it's being multiplied to both parts. Okay, now what's kind of nice on this one is we didn't have to make any changes on the left-hand side because that already has a base of 3. So let's just go ahead and bring that down. And so we can see now that we've got the same base of 3 on both sides. And so now we just simply set the exponents equal and continue solving for x. Sometimes it's a little bit more work at the end to actually get x by itself, but we're getting closer here, finding out that x plus 2 equals 15x plus 3. All right, so to solve this, let's think about getting all of our x's together on one side. So I'm just going to move them over to the right-hand side. We'll keep our x value positive is what I like to do. And then we'll go ahead and get the number part on the other side. And don't be alarmed if it doesn't seem like to be that your numbers are working out perfectly. Like we said, there's a very good chance that you'll get a fraction for your final answer. In this case, we end up getting -1/14 as our final answer for x. All right, so looking at these next couple of equations, we're going to see very quickly that we need a new method to solve them. And so the thing is that the same base method, it doesn't always work. In this first problem, 4 to the x equals 9. Well, if we think about that base of 4 on the left side, we could rewrite that and turn it into a base of 2. 2 squared is equal to 4. But if you look at the other side, 9 cannot be written as a base of 2. 9, you can't write it as a base of 4. There's no way that we could get it to be the bases are the same on both sides. And so what we're going to do instead, we're going to use logarithms to help us. And so our first step is going to be taking the log of both sides. The thing is that the base of the log that we use is going to match the base of whatever number is holding up on the variable part. So because we've got 4 raised x to the power of x, ultimately we're wanting to solve for x here. And so because that's a base 4 right there, I'm going to do log base 4 of both sides. So let me just show you what this step looks like. All right, so I'm going to highlight here in orange, that was our original problem, 4 to the x equals 9. And because it's an equation, whatever we do to one side, we want to do that same thing to the other side. And the way that we choose the little base of the log is based on this number here, whatever number is holding up our x log. And that's because a log with the same base is going to undo an exponential that has the same base. So remember, these are inverse functions of each other. 4 to the x is the inverse of log base 4 of x. And so they cancel each other out. They undo one another. And so what we can do here with that log base 4 of 4 part is draw a little line through. They're going to cancel out. And the only thing that we're left with is just the exponent part. So we're just left with x. And so I'm going to make a little note off to the side here of what we just did to say that log base a of a to the x is equal to x. So as long as these numbers right here are the same, it was 4 in our case. It's not always going to be 4, but those will cancel each other out. Okay, let's talk about what we have left, though, in our equation. So on the other side, we still have log base 4 of 9. So this is something that we can evaluate pretty easily using our calculator. We learned on last week in the last lesson about the change of base formula. So that's one option for how we can get this answer out as a decimal. We know that on our calculator, the log key is log base 10. And so unless you have something that's log base 10, we need to use the change of base formula to type it in. So this is going to be rewritten as log base 10 of 9 divided by log base 10 of 4. So remember in this formula here, whatever the base was, because it's log base 4, the base part goes on the bottom. And really there's invisible 10s here. I didn't write them because it's the common log and we don't normally write it in if it's base 10, but that's really what it is. So here's how that looks on our calculator. So we're going to do log base 10 of 9, close the parenthesis around the 9, and then we're going to divide by log 4. Okay, and if we round our answer just a little bit, we can see, well, it's approximately 1.585. And we could think about checking our answer pretty easily here. If we actually just plug that x value back in to the original equation, that means that 4 to the power of 1.585 should equal 9, or approximately 9, because remember, we rounded a little bit. So here's what that step would look like if we check our answer. Mine's probably going to be a little bit off, but we can see that, yes, it is essentially equal to 9. All right. Let's take a look at the next problem we have over on the right-hand side. Now, before we introduce the logs, before we take the log of both sides, we have to have the exponential part, like, completely by itself. So the piece that's holding up the exponent, we don't want there to be anything else on that side of the equation. So notice that we need to get rid of this minus 5. So let's go ahead and add 5 to both sides. Okay, from here, I'm going to actually give you a few minutes. I want you to try the rest of the problem. Let's see if you can finish this one. All right, so one thing different on this one is we have a base of 3. So notice how we have a 3 that's holding up the exponent part where the variable is. And so to get rid of that, to cancel that out, we are going to do log base 3 on both sides. So really the first step of showing my work, I'm just going to recopy exactly what I had in the previous step. I'm just putting a log base 3 in front of both sides. Okay, and then here's the fun part. So log base 3 of 3 holding up an exponent, well, it's going to undo the exponential part. So it's going to allow us to cancel out that 3. And we're left with the entire thing that's in the exponent. So it's the entire x plus 1, regular size now, that's left over. And on the other side, that's equal to log base 3 of 12. Now, there's a couple of ways you can do this. If you want to go ahead and evaluate log base 3 of 12, like we did on this one, and get a decimal, you can do that and then just subtract 1 from both sides. Or you can actually do it all at once. So an option for how this could look, if you type it in all at once, is you've got log base 3 of 12, and then it's minus 1 on the end of it. It's super important to know that it's not subtracting 1 from the 12, so it doesn't turn into 11. The minus 1 is completely separate at the end of whatever answer we get for the log part. Now, if I was using the change of base formula for this, I would type it in as log base 10 of 12 divided by log base 10 of 3. Make sure that we close both of the parentheses here and there. And then you could actually still type in the minus 1 at the end and still do this all in one step. If you're nervous about it, you can do like pieces at a time and then subtract 1 separately. But here's what it could look like all together. So I'm going to do log 12, close the parentheses, divided by log 3, close that parentheses, then we have minus 1. Just like this. And our calculator gives us, it's about 1.26. All right, now even though this equation had a little bit more going on with it than the first one, it's still a good idea to check our answer, plugging it back into the original equation. So this is saying that 3 raised up to the power of 1.26 plus 1, and then subtracting 5 should equal 7. And so we can do a quick check of that here on our calculator. So I'm going to do 3 raised up to the power of 1.26 plus 1. So notice I'm keeping that up in the exponent. If your calculator doesn't look like mine, you might want to just type in 3 raised up to the power of 2.26. Just combine that together for the exponent part. And I'm going to bring it down to regular size. When I subtract 5, it's a little bit off from 7 because we rounded our x value answer, but notice how it's very close. It's essentially equal to 7. All right, so that is how we can solve using logarithms. Sometimes I call this the log both sides method, and this actually works 100% of the time. So it's especially helpful if you cannot do the same base method. All right, so we're going to look at one last problem here. In number 7, we are going to think about making an investment of $200. So initial deposit of $200 is invested, and it's growing at 6.5% every year. We're going to start by writing a function that gives the amount of money, A, for T number of years. And really this is going to go back to how we were writing equations for real-life situations back on the very first day. We know that our exponential functions have this kind of general format that's a times b to the x. A is always the starting amount. So in this case, our starting amount was $200. And then b is what we call our growth factor, if it's growth. And that's what we multiply by each time period. So in this case, it would be every year. So if we had a percent increase of 6.5%, to turn that back into our growth factor, we're going to turn this percent into a decimal. So it's going to become 0.065, but then we have to add 1 onto it. So 1.065 would be our growth factor if we continually to multiply our dollar amount by that. That's going to simulate growing by 6.5% every year. I'm just going to make a little note here that x, in this case, represents the number of years. Oh, I totally didn't use the variables that it said to use, but a would be like where the y is, and then t would be where the x is. Okay, so using the skills that we have today, we're now going to be able to determine how long it's going to take this balance to grow to $400. So let's go ahead and replace the amount side, which is the y side, with 400. All right, so we know that we have an exponential equation that we're solving because the value of the location of our variable, the location of the x, it is in the position of an exponent. Before we apply one of our methods to solve, we do need to get this base, holding up the exponent, completely by itself. So in this problem, how can we get rid of the 200? What can we do there, Chris?
Divide both sides by 200.
Perfect. We'll go ahead and divide it out. That 200 is being multiplied in front. So to get rid of that, we're going to divide. So that 400 divided by 200 works out really nicely to be 2. And now the equation that we're solving, we've got 2 equals 1.065. Raise that to the power of x. I'm going to give you a few more minutes again on your own. I want you to go ahead and finish solving this equation, and that's going to tell us the number of years to get to $400. All right, so thinking about our two methods, we definitely would want to do our log both sides method here. It would not be possible or easy for us to get both sides written as the same base, so that's not always going to work. But we can always do the log both sides. Now, in this case, on the right-hand side here, the part that's holding up the x is the part that we want to cancel out, and it's 1.065. So that's going to be the base of the log that we're doing on both sides. So we're going to do log base 1.065 of 2. And then on the other side here, we're doing log base 1.065 of 1.065 raised up to the x. So as long as these two are the same number, the base, and then the very next number that's listed, that's holding up our exponent, as long as those are the same, they're going to undo each other. So that part is going to cancel. We're still left with x, so I still want to write that x down on the next line. And now it's just going to my calculator to evaluate this left-hand side. So I'm going to do the change of base formula again. So I'm going to type it in as log 2, log base 10 of 2, divided by log base 10 of 1.065. All right, and when we type that into our calculator, what we're trying to figure out here is approximate number of years. So that's going to look like this, and if we round that, we can see that this is about 11 years. All right, so we have our little quick notes box at the bottom of our paper today, and here we're just going to summarize, write out some of the steps that we did for our two methods in solving exponential equations. So what I'm going to do is put this as the title in the middle, and then we're going to branch off to two sides to show the two methods that we did. All right, so on this left-hand side, I'm going to title this is our same base method, which is what we took a look at on the front side. So with our same base method, actually either method, we're kind of looking for the same thing at the very start, is that we want to isolate the term with the exponent, which means we want to get that by itself. So in case you have something like a plus 1, like on the end, like we would want to subtract 1 from both sides first before we move forward with the method. So we want to get that term by itself, and then our second step was just to rewrite both sides with the same base. Once we did that, we just simply set the exponents equal. And then our last step was to solve for the variable. So one thing I think about with the same base method, if we have something like b to the n set equal to b to the n, as long as the bases are the same, then we say that m equals n. We just set our exponents equal. All right, so then we saw that our same base method doesn't always work, and so we have another option. So I'm going to say the other option over here is using logs. All right, so really similar first step here is we're going to isolate the base holding up the exponent part. In other words, isolate the term with an exponent, just writing it out a little different way. And then what we saw is that a log undoes an exponential with the same base. So if we have something like a to the power of x is equal to b, all we need to do here on both sides is log base a. And on the left-hand side here, the log base a of a to the x part, everything will cancel except for x. So log base a of a, those are going to undo each other. So it's really just that x is equal to log base a of b.